You are still muted, Dunyu.
Okay, can you hear me now?
Yes, now it's okay.
Okay, great. So thanks, Bin, for the introduction to the traction at a split node technique and how it is implemented with the read and the state friction. It is a really critical technical milestone for EQdyna, and it transformed EQdyna from previous sleep weakening law and to the experimentally based redundancy friction, and then open the opportunity for other cycle simulations. And all my work is based on being a redundant state friction implementation. I build on top of that. And in this talk, I will more focus on the applications and about the ground shaking from scenario earthquakes. So it's really hard to predict when and where an earthquake would happen exactly, for example, in the short time. But we can predict what would happen, with scenario earthquakes. For example, in this paper by Dr. An Yin from 2014 and from multiple data sets, and they've judge, there is a seismic gap near Tianjin. Is a really important city in China, and it has been muted for a long time, and there is a 160-kilometer seismic gap. But we don't know exactly when an earthquake would happen over there in the short time, but there were a lot of historical earthquakes in that region. But we can simulate scenario earthquakes and to estimate the ground shakings from the scenarios. And there are several keys, and we need dynamic rupture force. And here we use EQdyna, and we need 3D velocity structures and also waves, and we need to be able to simulate waves and attenuation and set responses and complex interactions between all these factors. And here we use the random fractal stress realization, and we also focus on the basin effect near the Tianjin seismic gap. So this paper, there are two papers by Dr. Duan and me. So this figure in the middle shows the rupture time contour of several scenario realizations. And rupture time contour, for example, the contour lines here shows when a rupture arrived at that location on the fault. And we have, I think, six scenarios with fractal random initial stress conditions based on the method proposed by Barr and Andrews 2011. It is a really nice method to generate random scenarios for dynamic ruptures. And you can see in the contours, and there are jumped, triggered, and delayed ruptures. The rupture process is really complex from these fractal generations. And at the bottom too, those are the reference models, and the stress conditions are homogeneous along the strike. And you can see the rupture process is much more smooth. Oh, here, can you see my mouse? I was talking about these two. And the above six are random fractal initial stress conditions. And we have a target magnitude about 7.5, and that's based on the estimates from geologic and other data sets from Dr. An's work. And on the right figure, on the red panel, shows the sleep distributions of these earthquakes. And also the magnitude of detailed earthquakes are shown in the figure panels. And an important results from this study is the basin effects. Where basin is you can imagine that is a softer material, and the waves comes into the basin will be trapped in it, and it will resonate. and cause stronger ground motions. And there are a series of studies to show that, to talk about it. Oh, sorry. And the figure here shows the research area. That's the THC fault. And the black solid line here is the Tianjin seismic gap. And the white contours are the isosurfaces of S-wave velocity of 1.5 kilometers per second. That's lower than the typical shear velocity of the crust. And you can see you can imagine that's the topography that go downward is for basin structures. And if you see the closed shape here near the Wuqing, that's one basin, and there's another one, and also there are two on the fault. So the velocity structure is independent from other data sets. So it's from tomography and other studies. And we need this kind of data set to see the basin structure. And then we combine the dynamic rupture with the basin structure and also the attenuation of the seismic waves. For example, here is the movie to show the one scenario. And on the top panel shows the rupture process. This is the fault surface. And then this is the nucleation location, and this is the Tianjin city, and this is the time, 1.4 seconds, and just started the earthquake. And then the sleep will involve, and the bottom three panels are the vertical velocities on the free surface. This is the fault parallel component, fault normal component, and also vertical component. And I'll play the movie. So you see the rupture starts and reaching the surface. This is the free surface. And at about 20 some seconds, the earthquake, the sleep evolutions has already stopped. And we have a magnitude 7.5 earthquake. And if we look at this area, the fault parallel component, and you see there is a still strong ground motions inside the Wuqing Basin. And you can see from the waves, the wavelengths of the waves are become longer. It's kind of elongated by the basin. And also here, the second basin will affect mostly the normal component. Let me go back a little bit. Okay. So you see the waves just arrived at the Wuqing Basin and also the Dacheng Basin. And you can see the wavelengths become longer by the basin. So that's really that's important for the earthquake engineering applications because really the structures will respond to different frequency contents of the seismic waves. And continue on that work, we have a simulated. We are building a simulated ground motion data sets. That's the DRV, dynamic rupture validation project. It's a big collaboration from researchers from multiple institutions, and the objectives is to to focus on the seismic hazard for high frequency ground motions for engineering designs. And what we want to do is validate the ground motion data sets with observations. And ideally, in the long term, we want to create a digital twin of a simulation-based data sets to supplement the lack of observation near the fault. For example, 2 kilometers off the fault, we don't have much strong ground motion data over there. And it's a collaborative approach. And so for this approach, we have some targets, kind of the simulation targets, but it's not like a verification effort. The targets are loose. Modelers, modeling groups are free to choose the best method even code and strategies for dynamic rupture source. And but importantly, we need to validate your models against observations. Here, the observation is another set of model, the empirical ground motion models from strong ground motion datasets. And for example, on the right shows the scalings. SA is the spectrum acceleration in G, and the horizontal axis is the periods. And we verify, you see, these are the multiple groups, research groups, and the results are overlapped with the ground motion model, the GMM, the gray area, and within one standard deviation. You can see the models are all produce comparable results with the data. So this validation is important because otherwise you don't know whether your model results, your simulations are real or not. So at least if your simulation can be validated against the data and observation, it means they are valid through those data sets. And you can see the source diversity is really high here. So these are the rupture sleep distributions from all the research groups. And so all these earthquakes can produce comparable results to ground motion models. And also, these are the ground motion, the spectrum acceleration on the free surface from all these models. And this would be useful for engineering applications because with looser targets, and we can capture more uncertainties from the ground motion simulation. And here is the scaling of ground motion from all the models at different periods. In engineering, earthquake engineering, we care about what period of the ground motion is. For example, this is the spectrum acceleration of 3 seconds, 1 second, and 0.3 seconds. And the bottom panel shows the intra-event standard deviation. And you can see the gray bar is 0.6, and that's from the empirical models. That means we don't have better characterization of that to reduce the uncertainty from the empirical data. And the other lines, color line, are for simulations. And this would be an area to make progress in terms of scientific progress, like what factors from the source or even the path or site can contribute to the intra-event standard deviation, and we want to reduce it. And the simulation now is not just about simulating an earthquake and get ground motion. We want to push it forward to a procedure. So actually, earthquake seismic hazard evaluation is a long producing chain. We need earthquake source, ground motion, and engineering applications. And for example, if you go downward, we may have PSHA, the probabilistic seismic hazard analysis, and even to create digital scenarios that has predicting power. And there should be no weak links in the procedure. And so we developed another open source platform, DR4GM, I mentioned previously briefly. And it's to streamline the dynamic rupture to engineering applications. So it will directly convert the results from EQdyna. And we are expanding the portfolio of software supported and from other dynamic rupture simulation code to ground motion metrics that can be directly used by the engineering community. And we are creating a simulation data sets that can be used by the engineering community. Okay, that's my talk on this part, and mainly about the applications of EQdyna dynamic rupture and in ground motion application. Thank you.
Thank you, Dunyu. Let's see, time-wise, probably we're about already hour or so. We're supposed to have a break. And Dunyu, so I think probably we can have 5 minutes break. And then I think for Dunyu on the schedule, I suppose you will give a demo. But how about we can combine